Good morning, everyone. It's a pleasure to open the session and share with you insights on GNSS interference, its impact, detection, and mitigation. This will be the outline of my presentation. I will start with a brief introduction on what is GNSS interference. Then I will introduce for you the SmartTrack Interference Toolbox, a technology designed by Leica Geosystems to mitigate RF interference. Then I will show you implications of interference on GNSS performance, and finally I will wrap up with a summary. What is interference for a GNSS receiver? So I would define it as a phenomenon where unwanted signals enter the receiver and disrupt its operation. This issue is becoming increasingly significant today for GNSS community for various reasons. One of them is that the diversity and the number of RF interference sources is increasing, such as, for example, satellite communication, sensor-to-sensor communication, intentional jamming, and military. Additionally, modern GNSS receivers are designed today with larger bandwidths in order to be able to track all visible satellites and signals. For instance, on the graph on your left, you can see the spectrum of a legacy GPS GLONASS dual frequency receiver where only tens of megahertz were needed to detect or to track GPS GLONASS L1 and L2 frequencies. In comparison, modern GNSS receivers with a full band GNSS requires hundreds of megahertz in order to track all the satellites, which makes these receivers susceptible to receiving these unwanted signals. The key question here is how interference impacts the GNSS receiver. So very often in the presence of interference, the GNSS receiver will have partial or total loss of log, it will have a reduced and or noisy carrier-to-noise ratio, and also its ability to track properly and to provide reliable raw observation data, RTK correction, or compute acquisition will be heavily impacted. In summary, we have three critical performance criteria are impacted when the presence of the interference. It's the ability of the receiver to provide raw data and the accuracy and reliability of this data. Taking that into consideration, we at Leica Geosystems, we think that RF interference and its various forms must be addressed when operating a CORS receiver right from the establishment of the station. This is why, to monitor, detect, and mitigate interference, we released since 2018 a technology, the SmartTrack Interference Toolbox, specifically designed to deal with this problem. This solution is available on all Leica GNSS CORS receivers, and it's mainly formed from three functionality. The first functionality is a frequency power spectrum analyzer that measures and outputs the radio frequency power spectrum on all GNSS bands. This will give the receiver the ability to monitor the spectrum. The second functionality is to automatically detect and instantly notify operators about the presence of the interference. This will give the ability of the receiver to detect and alert. And finally, if there is an interference, the interference toolbox will allow the operator to mitigate this interference, which gives the receiver the ability to mitigate and protect. In order to demonstrate for you better the functionalities of this interference toolbox, we conducted an experiment here at our headquarters in Switzerland, east of Switzerland, where we used one of our GR50 receivers, a CORS receiver, and generated two interference signals, one to interfere with Galileo E1, GPS L1, and one to interfere with GPS L2. I will show you in the next slide the comparison results in the presence of the interference and mitigation, but first I want to show you some of the functionalities of the interference toolbox. So quickly here on the top graphs we have the spectrum analysis, the output of the spectrum analysis of the GR50 receiver. I put on top of the graphs the minimum bandwidth required to track properly the GPS L1, Galileo E1, and GPS L2, and we can see the spike. So the spike here, this is the interference on L1, and here is the interference on L2. And we can see its closeness to the minimum bandwidth required. For instance, for example, for GPS L2, we can see it's within the minimum bandwidth, which obviously will, as we will see later, will impact the tracking more. On the lower graph, it's a different representation, but the same data. It's a waterfall, so you can consider it like a heat map where darker the color is more the power is concentrated on this frequency. And here we can see the presence of the interference where it's in this dark red color while all the rest of the spectrum is blue. In terms of detection, this is a snapshot of the receiver web interface. We can see that the receiver was able to detect the interference and provide some additional data, such for example the center frequency, the bandwidth, the power, also the power spectrum density. All this information that will be generated by the receiver will be wrapped up in an email and sent instantly to the operator to notify about the presence of the interference. And finally, for mitigation, so we used here a notch filter. We can see the shape of the filter to attenuate the power where the interference is. And then we can see here on the waterfall plot that where there is interference, it's now blue, and most of the power now is focused where there are the GNSS signals are transmitted. So basically what we did here, we attenuated the power on the interference, and we focused most of the power where the GNSS signals are transmitted. So in comparison results, on top graph we see the average number of tracked satellites. So we did the experiment over 9 hours, and we can see that the average number of tracked satellites when there was no interference was around 30, and then it dropped to by 4 satellites to 26, and then with mitigation we gained another 3 satellites. For tracking performance, we went from 85%, which is the total number of observation over the total number of expected observation. And we see here in Switzerland we are surrounded by mountains, so it's very hard to track 100%, but without interference we're at 85, and then the number dropped to around 70%, and then increased back to almost 85. In terms of flag loss of log, we see that when there was no interference, most of the flag loss of log are happening at lower elevation, as we can see here, and this is the expected behavior in open sky condition. With interference, it's happening over all elevation, and then with mitigation again at lower elevation. It's important to note here that the presence of interference doesn't necessarily increase the number of loss of log, but will definitely change the nature of its occurrence. So from only low elevation to all elevations. In terms of signal to noise ratio, so the unpacked signals, we lost around 4 dB on L1, 11 dB on L2P, and 9 dB on L2C. And then with mitigation, we gained back most of the SNR lost on the signals. Finally, in terms of positioning, we did the same test where we had a reference station in Bregenz. It's almost 15 kilometers from our headquarters. The reference station is located in Austria. And then we had a rover operating in our headquarters. And then we jammed the reference station, not the rover. So the reference station was jammed, and we did the positioning test on the rover to see what's the impact on the rover when it's receiving data from a station which is under an interference. So here we see an overlap of the 3 tests done. So if I separate them, we see that the accuracy was within plus or minus 2 centimeters in the north and plus or minus 1 centimeter in the east, which are expected when there is 15 kilometer baseline. And then we clearly see when there was interference in the blue that the accuracy has dropped significantly. And then with mitigation, we have more or less similar performance. If I dig deeper into these numbers, in terms of accuracy, we see that it's almost doubled on the horizontally on the east and north, and then on the vertical we have even almost tripled the accuracy. In terms of reliability, we see that we went from 1 centimeter to 2 centimeters with the presence of a jammed reference station, and back to 1 centimeter with mitigation. And finally, with availability, we were 100% of the time we had a precise position, fixed position, that dropped to 90%, 92%. This is over the 9 hours, it's around 45 minutes, which means the rover was 45 minutes not able to compute the position, even if it's operating in open sky. And then with mitigation, we see that the number is back to 100%. To summarize, the key benefits of using an interference detection and mitigation solution on board the GNSS receiver is you save time and cost, because no additional hardware is needed to detect interference. You don't need to displace your reference station, and you don't need to temporarily shut it down in case of a heavy interference. You will ensure 24/7 availability, satellite tracking, row observation, and high-quality, precise positioning. And finally, it will open up new opportunities, such as an easy and an affordable way to implement a country-wide grid of RF interference mapping tool. And on this note, I want to end my talk to show you an example from Romania, from the Rompos network, which is a governmental network for the Cartography Center of Geography. They designed, based on the interference toolbox, the interference mapping tool to monitor and analyze interference in Rompos network, helping users understanding disruptions, anomalies, and signal reception. It's an online tool. You can access it using this website here, where you can see overall around 80 to 85 stations in real time, the presence of interference and its impact on the station. And I'm perfectly on time. I would like to thank you. And I will be here all day, and we will be all having a stand also this afternoon. So maybe we don't have time for questions, but you can reach, and we have. So if you have any questions or not, you can ask me in the afternoon.